So this is just a short video, a short digression in regards to orthonormal bases and their corresponding counterparts, ordered bases. So as we've established earlier, orthonormal bases merely refer to a set of some n-unit kets, that are mutually orthogonal to one another. And the key word here that we're going to be exploring a little further is that these consist of a set of kets. And so when we typically write sets, as you may be familiar with, we put them in curly brackets, curly braces, depending on what you want to call them. And let's say we have like B1 and some ket B2, and it's quite straightforward, right? And as you may know or may not know, simply put, this set of mutually orthogonal bases is fundamentally equivalent to if we take another permutation of all the elements within this set. So if I flip their places, make it B2 and B1, they are ideally identical to one another. The characteristics do not change. In short, if you have a set of these kets, their order, regardless of whatever permutation you might be looking at, it doesn't matter. It's merely a collection of data. Now, if we want to consider something known as ordered bases, however, all of a sudden the order, as the word ordered implies, all of a sudden the order, the permutation that we're looking at does indeed matter. So if you actually consider and kind of expand upon this phrase itself, you might notice that ordered bases kind of sound a little bit like ordered pairs. So maybe if you've done graphing before, ordered pairs, right? Maybe graphing in, say, 6th grade, 7th grade, 8th grade, any middle school or primary school, depending on precisely, what level you're at. Ordered pairs referred to the location of a point on a given graph. So oftentimes you'd write it as x, y, right? And it shares that same first word. So when we look at ordered pairs, this point, x, y, right? X units in the x direction, y units in the y direction. This is your final point right here. Right? This point was not equivalent. It is not equivalent to some other ordered pairs, say yx, right? Because yx in this case would merely be something that goes y units in this direction and say x units in this direction. This is where your actual point is. And all of a sudden you find that these points are different, meaning that the order in which their coordinates are given to you does indeed matter. And so that takes us back again to ordered bases. Just as with ordered pairs, when we look at their components, indeed, the order in which they are presented does matter, and similar to ordered pairs, we do put them in parentheses. So say you have some ordered bases B1 and B2, right, and close the parentheses. This is fundamentally not equivalent to B2, B1. Right. So now let's take this and apply it to quantum computing. Let's consider what this means in terms of spin, as we established before. Orthonormal bases and essentially these sets and these kets are fundamentally representative and can be mathematical models for spin. And so when we consider something like some orthonormal set with spin up and spin down, right? It merely tells us spin in the vertical direction. So it's telling us that when we measure something, it's going to be in either 0 degrees, right, or 180 degrees. And our measurement, our apparatus is telling us something along those lines, right? The particle either be deflected upwards in the Stern Gerlach apparatus or deflected downwards. It either has spin up or spin down. So this is, simply put, equivalent, once again, right, is equivalent to if you mix up the precise order of these. However, if we take the ordered bases version of this, right, and we write it such that we have, say, spin up coming first and then spin down coming second, or the ket representing these types of spins coming second, this actually is once again not equivalent to something like this, where their orders are switched. Right, and in the context of quantum computing, looking at something with this right, where we denote their spins using this, will correspond to measuring the spin of this particular particle where the south magnet is on top. So as a reminder, you're given, let me use a different color, your particular Stern-Gerlach apparatus perhaps looks something like this, right? And what this here implies with this ordered bases is that the south magnet indeed falls on top and the north magnet is on the bottom. So the particle, what we're referring to as quote-unquote up and quote-unquote down, is formally defined. And similarly, if we look and define this with spin down in the first place of your ordered bases implies is that we are indeed looking instead at apparatus where south is on the bottom and north is on the top. So simply put, depending on precisely how we present these bases, the meaning behind them and the meaning implied will vary. So that is something to be aware of. All right, and that's it for today. As always, stay curious, keep on learning. Thank you.